Now let's clean all this mess up and let's go on and do the exact same thing with our second derivative. We set the second derivative equal to 0 and we're going to solve. Now realistically, at any rate, you're going to get your zeros when this polynomial equals 0. And that was complicated. I chose not to do that in my head, of course. I put that into an algebra calculator, and you get that occurs at x equals negative 14.26. So now we're going to take that and we're going to set up a table again. We're going to do negative infinity to negative 14.26. And now here's where the trick comes in. You do negative 14.26 to negative 2, negative 2 to positive 2, and positive 2 to positive infinity. Now you may be wondering to yourself, how come I picked these numbers here? Where did the negative and positive 2's come in? Well, they're asymptotes. If you factor the bottom here, this is equal to 2x plus 10 divided by x minus 2, x plus 2. Wherever you have a 0 in the denominator, you have an asymptote. And wherever you have an asymptote, you have to include that in your table in the second derivative test. You don't need to do that in the first derivative test, but it's important you do it in the second derivative test. So that's where those come from. Now we'll pick some test values, negative 15, negative 3, 0, and positive 3. And then you put those test values back into your second derivative, which of course I didn't do. I put them into a calculator. I got negative 5.93 times 10 to the negative 5. This is 2.944. This is negative 1.25. And this is positive 6.976, assuming I got these right. So this is negative concave down, positive concave up, negative concave down, and positive concave up. So this allows us to know where our inflection points occur. Our inflection points are whenever we switch from concave up to concave down, but inflection points do not occur at an asymptote. Because at, say this is our negative 2, this is our positive 2, we might have something that looks like this beforehand and something like this after. Well, there's no inflection point here, it just jumps, so asymptotes don't count. So this is not an inflection point, this is not an inflection point. The only inflection point that occurs is at negative 14.26. So your inflection point equals x equals negative 14.26. You're decreasing before the IP. You're concave up until your asymptote. You're concave down to your second asymptote. And you're concave up after that. So we'll make that note there. And now I'm going to clear up some room. Alright, so now we know minimums, maximums, inflection points, and we know our asymptotes. Now we're going to need to know our x-intercept. X-intercept is going to occur where this function is equal to 0, which clearly is going to occur at negative 5. We can figure out a y-intercept, which is where you set f of x is equal to 0. So 2x, our y-intercept occurs where we plug in x equals 0. So f of 0 is equal to 2 times 0, positive 10, over negative 4. So equals negative 5 halves. It's useful to keep that around. And the last few things we need to know is the y values of our minimums, maximums, and inflection points. So that occurs when we put negative 14.26, negative 5 plus or minus the square root of 21 into f of x. And I'm going to pause it, put it through my calculator, and then I'll come back with the answers. Alright, I'm back from my calculator. The inflection point, which occurs at x equals negative 14.26, has a y value of negative 0.93. The minimum, which occurs at negative 9.58, has a y value of negative 1.04. And the max at negative 4.2 and negative 2.396. Alright, and we know our asymptotes, maybe two S's, spelling, that occurs at x equals plus 2 and negative 2. And then we have our x-intercepts and our y-intercepts. So let's say each one of these, well, we have 5, and I need to go up to negative 15. So this is negative 15, negative 3, positive 3, positive 15. And I only need to go down to negative 3, positive 3 here. Alright, so let's start doing some graphing. X occurs at negative 5, which is right about here. We have an inflection point at negative 14 and negative 0.01, which is way down here. A minimum at negative 9, 0.58, and 0.1, negative 0.1, which is about there, not to scale, of course. Maximum at negative 0.42 and negative 2.396, so that's about here. We have vertical asymptotes at negative 2 and positive 2. We have a y-intercept at negative 2.5, which is right about there. And we already covered the x-intercept. And now we also know that we're concave up, we're concave down until here. We're concave up until the asymptote, concave down after, and then concave up after that. We're decreasing until here. We increase until here, and then we decrease after that. So now it's time to actually take a sketch of this, and this can be a little bit of a challenge, but we can do it just the same. My guess is that this is going to decrease really slowly. So I'm going to draw a very, sorry. This is actually going to be pretty much a straight line. It's the only way to fit it. It's going to have just a slight tinge downward. And then right here, we're actually going to be curving. Okay, we're going to be curving down until we hit our minimum, and then we start curving upwards. Then we have an asymptote, so this is going to go to infinity. Down here, this is pretty easy. We're going to come up, cross to our maximum through the y-axis, and then down. And then on the x-axis, we're pretty easy too, because we're never going to cross it. We don't have any mins and max, so it looks like that. So the red's something along this line, and in fact, we can verify this with our graphing calculator. And it's really hard to notice the minimum and the inflection point on it, but just the same, that's about what our graph looks like. So that's this problem presented by www.free-academy.com.